Assalamu alaikum. I am Nahian Mustafa, registration number 2024 831043. Before discussing persistent segment tree, let's first understand the segment tree. A segment tree is a binary tree used for efficient range queries and updates. Leaf nodes represent individual array elements, while internal nodes store aggregated information such as sums or minimum values. It can be built in order of n time, and both queries and updates take order of log n time. The concept of persistence was normally intro- the concept of persistence was formally introduced in 1989 by Driscoll and his colleagues. Their work showed how data structures could preserve older versions efficiently. Over time, these ideas became popular in functional programming, competitive programming, and modern software systems like Git and databases. In a normal segment tree, every update overrides the previous state. Persistence solves this problem by preserving all historical versions. Each update creates a new version while keeping old versions accessible. This allows us to query past states, perform rollbacks easily, and support multiple readers without modifying existing data. A persistent segment tree works using two key ideas, path copying and structural sharing. During an update, only the nodes along the root to leaf path are copied. All unchanged nodes are shared between versions. Because of this, each update requires only order of log n additional memory and time. Starting from the original tree, every update creates a new version. Only a few nodes are newly created. While most nodes are shared with previous versions, we store a root pointer for each version, so accessing any version takes order of one time. To summarize, a persistent segment tree extends a normal segment tree by preserving every historical version efficiently. It, Here I will explain the build operation of a segment tree using the array 1, 2, 3, 4. A segment tree is a data structure that stores information about ranges of an array. During the build process, we repeatedly divide the array into smaller parts until we reach individual elements, then combine the result while returning back up the tree. We start with the entire range 1 to 4. Since start and end are not equal, this is not a leaf node. We calculate the midpoint, which is 2, and split the range into left 1 to 2, right 3 to 4. The function always processes the left side first. For range 1 to 2, the midpoint is 1. This creates two leaf nodes. Range 1 to 1 stores value 1, range 2 to 2 stores value 2. After both leaves are created, the parent combines them. 1 plus 2 is equal to 3. So the node representing range 1 to 2 stores 3. Next, we process range 3 to 4. Its midpoint is 3, creating two leaf nodes. Range 3 to 3 stores value 3, range 4 to 4 stores value 4. These are combined. 3 plus 4 is equal to 7. So the node representing range 3 to 4 stores 7. Now we return to the root. The root has left child is equal to 3, right child is equal to 7. Combining them gives 3 plus 7 is equal to 10. This is the sum of all elements in the array. The segment tree is now fully built. The build process follows the simple steps. The build process follows three simple steps. 1. Split the range into two halves to recurse until a single element is reached. And 3. Combine child values while returning back up. This is why segment trees are often described as a divide and conquer data structure. In C, the segment tree is usually stored in an array called tree. The build function stores the array value when start equal equal end, otherwise finds the midpoint, recursively builds the left and right children, stores the sum of both children in the current node. The left child of node I is at 2i and the right child is at 2i plus 1. The build operation runs in order of n time because each node is visited only once. To summarize, the segment tree build operation works by split, recurse, and combine. Using the array 1, 2, 3, 4, we build a tree whose root value is 10, representing the sum of the entire array. Thank you.
Hi, my name is Argo Vishwash. My registration number is 2024831049. So here I'm discussing about update operation of persistent segment tree. Now here we are using a special technique called path copying. Now we are taking a 8 sized array and then we are converting it into a segment tree. Now what? Now here at the last element, we choose at the last element, which is 8, and we want to update it to 9. Now here is the descent phase. Now in this path copying in this path copying system, if we created several in this path now in this path copying system in this path copying system, uh, if we update an element, we don't modify the real tree. Rather, we create a different or new version of the tree. That means if we have updated the tree 3 times, that means there's 3 more version of the tree available. Now we are at root, which currently holds some 36. We allocate a brand new node to serve as the new root for version 1. Since index 8 is in right half and the left is simply shared, we point the new root's left pointer directly at the old version 0. Then we then recurse the right side. We now at 5 8. Now the sum is 26. Now again we allocate a new node at index 8 is in the right half, so 5 comma 6 is shared, so we recurse right into 7 comma 8. We are at 7 comma 8 and sum is 15. The new node is allocated, index 8 is on the right, so left child leaf is value in a leaf with value 7 is shared, so we recurse right. The path copying is in action. At every level we create one new node, copy the pointers from the old node, and then immediately shared site we are not going into. Now here we have reached the leaf node, and it's our targeted node. The base case leaf equals right, so we know we are the target. We create a leaf node and set its value to 9. The descent is complete. Now we call stack stars to unwind. Now the recursion returns back up and each node recalculates the sum. The left child is 7, so the new child is 7 plus 9 is 16. Thus we update each empty node. Now here is our final segmentary version, and here is the code of the segmentary here's the update operation code for segmentary in C language. Now here is our version 1, means the updated version, and our time complexity for the segmentary. To summarize the complexity, each update runs on big O log n time and uses big O log n extra space. The initial build takes big O n space, and addressing any version is big O 1. Just index onto roots array.
I'm Abil Wakar Jihan, registration number 2024-831-042. Today I'll be presenting on the query operation of the segment tree, specifically how it answers the range sum query efficiently without scanning every element in the array. The problem is simple to state. Given an array A, find the sum of all elements between index I and index r. The naive approach scans every element in that range, which takes order of n time. A segment tree does the same thing in order of log n, and the key to that is how the query traversal works. At any node during the traversal, there are exactly 3 possible situations. Either the node's range is fully inside the query range, in which case we return the node stored sum immediately and stop, or the node's range is completely outside the query range, in which case it contributes nothing, so we return 0, or there is a partial overlap, in which case we split. We recurse into both children and add their results together. That's the entire logic. Let's walk through a concrete example to see how it plays out. Our array is A is equal to 1, 2, 3, 4. The query is sum over the range 0 to index 2. The correct answer is 1 plus 2 plus 3 is equal to 6. We begin at the root, which covers the full range index 0 to 3 and stores the total sum of 10. We compare the node range index 0 to 3 against the query range index 0 to 2. The node extends to index 3, which is outside our query, but index 0 to through 2 are inside. So this is a partial overlap. We cannot return the stored value 10 because that includes third index of array A, which we don't want. So we split. We compute mid is equal to 0 plus 3 divided by 2 is equal to 1. It recurs into both the left child index 0 to 1 and the right child index 2 to 3. The root will combine whatever those two calls return. We're now at the left child, which covers index 0 to 1 and stores the value 3, which is 0th index of array A plus 1th index of array A is equal to 1 plus 2. We compare index 0 to 1 against the query index 0 to 2. The node range 0 to 1 lies entirely within index 0 to 2. This is the fully inside case. We don't need to go any deeper. The entire subtree rooted here is within our query range, and the stored sum already represents exactly what we want. So we immediately return 3. This is where the segment tree earns its efficiency. By pruning whole subtrees in a single step, the two leaf nodes, 0th index of A and first index of A, are never individually revisited. Running total so far 3. Now we visit the right child, which covers index 2 to 3 and stores the value 7. That's second index of array A plus third index of array A, which equals to 3 plus 4. We compare index 2 to 3 against the query index 0 to 2. The overlap is only partial. We want index 2, but not index 3. So this is another partial overlap. We split again. Mid is equal to 2 plus 3 divided by 2 is equal to 2. We recurse into left child index 2 to 2 and right child index 3 to 3. For leaf node index 2 to 2, the range 2, 2 is fully inside 0, 2, 0 through 2. So we return its value, which is 3. For leaf node range 3 to 3, the range 3 to 3 is completely outside index range 0 to 2. Index 3 is beyond our query boundary, so we return 0. Right child subtotal 3 plus 0 is equal to 3. Now the recursion unwinds. Each call passes its result back up to its parent. The left child index 0 to 1 return 3, the right child index 2 to 3 return 3. The root combines them, 3 plus 3 is equal to 6, and we can verify 0th index of array A plus first index of array A plus second index of array A is equal to 1 plus 2 plus 3 is equal to 6. Correct. Notice how many nodes we actually visited. Root of 0 to 3, left of 0 to 1, right of 2 to 3, leaf node 2 and leaf node 3. That's just 4 nodes out of 7 total. And we never touched 0th index of A or first index of A individually. The fully inside pruning at from range 0 to 1 saved us those 2 visits. Now let's talk about the code. It's a C code implementation. The function query takes the current node, the node's range start to end, and the query range L to R. The first condition handles the outside case. If the node is null or the ranges don't overlap at all, we return 0 immediately. The second condition handles the fully inside case. If the node's range is completely covered by range L to R, we return node's value without going deeper. Otherwise, we hit the partial case. We compute made, recurse into both children, and return the sum of the two results. The recursion naturally assembles the answer bottom up as the call stack wins. The code is clean and mirrors the three case logic exactly. There's nothing else to it. So to wrap up, the query for sum 0 to 2 gives us 6, reached by visiting just 4 nodes and combining their results. The traversal followed this path. Root was partial, so it split. Left child 0 to 1 was fully inside, so it returned 3 immediately. Right child 2 to 3 was partial, so it split further. Leaf node 2 was inside and returned 3. Leaf node 3 was outside and returned 0. Final answer 3 plus 3 is equal to 6. 3 takeaways. First, 3 cases decide everything: inside, outside, and partial. There's the complete logic. Second, subtree pruning is the source of efficiency. Fully covered nodes return instantly without visiting their children at all. Third, the cost is order of log n. At most, order of log n nodes are touched per query, compared to order of n for a linear scan. And finally, this query traversal follows the same shape as the build and update traversals. Once you understand one, you understand all three. That concludes my presentation. Thank you.
My name is Fayaz Abid Muhim. My registration number is 28 and I am covering the logical deletion operation part of persistence segment 3. In a persistence segment 2, we perform a logical delete using a tombstone instead of physical removal. We mark a node as deleted by setting its value to 0, ensuring all versions remain perfectly intact. In this slide, to delete key 4, now we create version 1. We clone the root where its left subtree to the shared version 0 node and recurse right. We continue to clone nodes along the path to leaf 4. Any subtree not on our direct path is wired directly to the existing node from version 0, which is the secret to keeping this persistent and efficient. Upon reaching leaf 4, we create a brand new node and set its value to 0. This is a tombstone. The original leaf 4 in version 0 remains untouched. As we return upward, we recompute the values of our clone parents node. For instance, at node 7, we take the shared value 3 from the left and our new 0 from the tombstone to update the parents sum to 3. The final version root now reflects the deletion. Version 0 remains completely unchanged, and version 1 holds our tombstone. Every version stays permanently queryable because we never touch the old ones. This is the first final version. In the code part, this is our parameters. This part creates the node and it's the base case. It This is whether we will go left or right. If we go left, it wires it wires to the past one and it wires to the right one, and these are the recursive code. Now we will talk about lazy propagation. Now, a standard segment tree handles range queries efficiently, and a persistent one takes this further. Every update creates a new version, allowing us to query any past state at any time. We achieve this through structural sharing, only cloning the nodes on the update path while sharing the rest. In the version 0, our base state, every node has a value and a lazy tag, both set to 0. When we perform our first update, say adding 5 to indices 1 and 2, we don't touch version 0. Instead, we clone only the nodes on the specific path. If an update fully covers the range, we stop recursing, store the lazy value there, and update the node sum. This is the essence of lazy propagation. Deferring the work any node not on the path is simply reused from the previous version, keeping memory uses to just o log n per update. When we create version, this is the version 1, and here we change index from 1 to 2 and added 5 in the initial version root. We added 15 because there are three nodes below it that we had to change. And when we went to left, this the query area proper you overlapped the index number, so we just added the value and added a lazy element 5. In the right side it partially covers the element, so we go to the left and right. In the left it fully covers the index, so we add the value 5 and lazy element, but in the right side we see that it does not cover our initial index, so we skip it. Now we create version 2, we must encounter an existing tag from version 1. We simply push that down before applying the new update to query. You pick the root of the version we care about and traverse. If a node's range is fully covered, return the value. If it's outside, ignore it. If it partially overlaps, push the lazy tag and recurse. Because we never mutate in place, every version remains perfectly preserved. In this, we will talk about in in this we will talk about multi-version query. Mm, Three independent version roots all pointing into the same underlying tree, version 1, 0, and 2, each with their own nodes. And this will take time complexity of O log n. When we query the sum range of 1 to 2, 1 to 2, we start at version 2's root. It partially overlaps with 1 to 2 index, so we can't return directly. We call push down to apply any pending lazy. Then split the query, recurs into the left child of for index 1 and the right child for index 2. The outer nodes, the index 0 and index 3, are completely outside our range, so they get pruned immediately. Now we collect the results on the way back up. From the left subtree, index 1 is covered and returns 0. Index 0 is disjoint and skip. From the left subtree, index 2 is covered and returns 15. Returns 15. Index 3 is disjoint, skip, and it is skipped. Combine on the way up. 0 plus 15 is equal to 15. That's our answer. If we had queried version 1 or 0 instead, we would get the same. In the final the code three functions: push down, update range, and query. Push down clones the code, zeros its lazy, then clones both children and forward the pending lazy to each, stacking it onto their value and lazy fields. Update range has three cases: out of range returns the original node unchanged. That's our structural sharing. Fully covered clones the node, bumps value and lazy, and stops. Partial overlap calls push down, recurses both sides, and recomputes the value on return. Query range mirrors the same three-case structure. Out of range returns 0, fully covered returns node's value, partial overlap pushes down and sums both children. Every function allocates new nodes on the path. Nothing is ever mutated. Thank you for your time.
I'm Awil Walker Jihan, registration number 2024-831-042. Today, I'm going to walk you through some of the most powerful real-world applications of persistent segment trees, a data structure that lets us keep a full history of changes without wasting memory. Let's start with something we all use every day: Git. Every time you make a commit in Git, it doesn't copy the entire project. Instead, it creates a new persistent tree version. Only the files that change become new nodes, while unchanged files simply share pointers with the previous version. This is exactly how a persistent segment tree works. That's how Git supports instant rollbacks, branching, and structural sharing, all in constant or logarithmic time, without duplicating your entire code base, of course. Moving on. The same idea powers database snapshot systems. Databases like PostgreSQL and CockroachDB use persistent tree structures to maintain multiple consistent snapshots simultaneously. Every transaction creates a new root. Older roots stay valid for read queries with no locking required. This is called MVCC, multi-version concurrency control. What this means in practice, you can query what the database looked like at any past timestamp, roll back to a previous state in order of one time, and maintain a full audit trail, which is a legal requirement in industries like finance and healthcare. Now let's talk about where computer science students most often encounter this structure: competitive programming. The most famous problem is kth smallest in a range. Given an array, find the kth smallest element between indices L and R. The solution builds one persistent tree per prefix of the array. To answer a query, you just take the difference between two versions, result, order of n log build time, order of n log n build time, and order of log n per query, which is essentially optimal. The same technique handles range frequency counting and dynamic range sum queries across multiple historical versions of an array simultaneously. Persistent segment trees are one of the sharpest tools in competitive programming. Here's another application you interact with constantly: undo and redo. In text editors, design tools, and spreadsheets. Applications like Visual Studio Code, Figma, and Adobe Photoshop use persistent data structures so that every edit creates a new version. Undo simply moves the pointer backward, redo moves it forward. No data is ever copied or recomputed. The entire history is preserved, and because unchanged parts of the document are shared between versions, the memory cost per edit is only order of log n new notes, not a full copy of the document. This is why modern editors feel instant even with hundreds of undo steps. Thank you for your time, everyone.
Now let's look at the numbers. A persistent segment tree has big O n find time, big O log n par query and update, and big O n log n space complexity for all version. Compared to naively copying the array for each version, which cost big O n Crosby space, this is a dramatic improvement. The key advantages are full version history, big O1 rollback, concurrent read access with no locking, and structural sharing through immutability. Now, let's talk about the disadvantages or the trade-offs. Now, of course, there are some trade-offs. Memory uses is n-log-n higher than a standard tree. The implementation is complex because of the structure is pointer heavy and has poor cache locality, which means real-world throw output can be 2 to 4 times lower than a simple array-based structure. The rule of thumb: use persistent segment tree only when the version requires a hard requirement. Otherwise, a standard segment tree is simpler and faster. To summarize, the power of segment trees come down three insights. One, path copying is the core technique. Only big O log n nodes are duplicated per update. Everything else are shared. Two, immobility is a feature, not a limitation. Once written, nodes are never modified, making concurrent trees safe and rollbacks trivial. 3. Pointers arithmetic replaces recomputation. Any past query is answered simply by routing the right version's root pointer. The single idea powers the version control database, snapshots, undo systems, and some of the most elegant solution in competitive programming. Thank you.